All right, so there's only a couple of new sections left to cover this year before we've really tackled everything they could ask you on the AP test. This isn't really even, in this section I'm counting, even though it's not really new. This is something we've done before on and off throughout the year. We're going to be talking about solving differential equations. Sometimes people forget what that means. To solve a differential equation is to simply come up with a parent function, including the plus c value, if you're given the initial condition. When they give you a derivative, be able to come up with the parent function. So your answer, if whenever they ask you to solve a differential equation, your answer is going to be an equation, specifically a parent function. Now, that's the good news. I guess the bad news, if it is bad news, is that there isn't one technique that gets used. This is actually kind of an opportunity to go back and review all the different integration techniques that we've looked at throughout the year, because they could throw about anything at you that would be fair game. So we're going to look at a couple examples today in the notes here, just reviewing different techniques of integration, because that's the kind of stuff that you'll see on the next homework assignment. So the first example here is a very typical looking problem for this section. It says, solve the differential equation, derivative of y with respect to x equals this fraction. That means find the parent function y, or f of x, if the parent function goes through the ordered pair -1, 1. That's what they're saying here. I'll find a pencil that isn't dull. Because this video is probably dull enough for all my pencils. Okay, so the first step in all of these problems is to separate the variables. Get your y's with your dy's, get your x's with your dx's. Can't do anything else until you do that step. So in this case, the dy is on top. I want to leave it there. I don't want my differentials in any denominators. So I'm going to bring this 1 plus y over. And I'm going to do that by dividing it away. If I divide the 1 plus y off of this side, it'll show up in the denominator of the left side. This dx, I don't want my differential down there. That's in a denominator. So I'm going to multiply it on to this side. There's already an x parked in the denominator here. I'm now going to have differential x on top of that fraction. Once you have the variables separated, then you can integrate both sides. You can't integrate if you have x's with dy's or vice versa. So I'm going to integrate both sides of this thing. U sub on the left side gives me, if I let my u equal the denominator, then my du is simply dy, and that's going to take care of the numerator for me. So if I rewrite this left side, I get du over u, which looks remarkably like what this side looks like, just with a different variable. Hopefully you remember what happens when you have to integrate du over u. If you don't, hopefully then at least you think of it as maybe like, oh, that's u to the -1, right? So then if I go up a power and over the power, I'd have u to the 0 over 0. Oh, wait a minute, I can't have a division by 0. That's right, this is a different, you can't do power rule on this. The reason you can't do power rule on this is because this is going to give you natural log in both cases, because they're both in the same form. So on the left side, I'm going to have natural log of u. I know there's a plus c here, but I'm just going to hold off and put the plus c at the very end of the right side. The right side is natural log of x. I'm going to combine all those constants into one term at the very end that I'm going to call plus c. Now, u, we should probably go and put back the variables that we originally had. 1 plus y is what we're going to put in for our u. Okay, we can't stop here. That's another, when they say solve the differential equation, notice they say y equals. They want the y isolated. We can't have y tucked away inside a bunch of other operations. So we're going to have to eventually go in and get that y out of that quantity and isolate it before our work is done here. A really good way to do that, because we have to get rid of natural log, is to write this exponentially. This is a base of e. Natural log is automatically a base of e. So if I were to write this exponentially, I would have e to this as a power would equal this quantity. Now looking at this left-hand side, we have e to a two-term exponent. Somewhere in your past math experiences, you've probably dealt with like properties of exponents. They say, ooh, if the base is the same and the bases are being multiplied, then you can just add the exponents. And that's very true. What we sometimes forget is that equations are a two-way street. If you have this, which we do here, you can also write it as base to the first term times base to the second term, which means this expression, e to the ln x plus c, could be written as e to the ln x times e to the c. That's how I'm going to write this. I'm going to cheat a little bit here. These absolute value bars are kind of they're not going to help me isolate the y. So what I'm going to do is I'm just going to say this is true for y being greater than -1. And that'll keep this quantity positive and therefore make the absolute value bars irrelevant. All right, back to this whole e to the whatever power. E to the natural log of something. E and natural log are inverse operations. So this expression here is simply just going to be absolute value x. E to the c. Look, e is a constant. C is a constant. If you have a constant to a constant, you just get a constant. So I'm going to cut right to the chase here, and I'm just going to call this times c, or better yet, I'll put c out front. And yes, I know this c is different than this c in full context. Fine, this is c1 there. If I want to isolate this y, I'd also have to subtract 1. And now what I have is the general solution to this function, or to this differential equation, I should say. To finish the job, we need to figure out what c is. To figure that out, we can plug in -1 for x and +1 for y. So if I plug -1 in for x, the result is a positive. If I plug in +1 for y, okay. So it looks like c is 2. Nope. Yes, it is. C is 2. I can't do math all of a sudden. Okay. So to finish the job, you want to write your entire equation complete with the plus c. We're going to have y equals not cx, but 2 absolute value x minus 1. That's what they mean by solve the differential equation. So the steps there, just to review, you needed to separate the variables. Get your x with dx and your y with dy. You needed to integrate. We needed to do some algebra to isolate the y. We needed to figure out the plus c value. And then finally, we needed to write the entire equation. The only non-negotiable in these steps, I would say, is sometimes you can swap the order for 3 and 4. Sometimes it might be easier to figure out what c is, get an actual tangible number in there, and then isolate the y. But otherwise, these are all steps you need to do pretty much in that order. So let's take a look at a different type of integration in a different example. Okay, similar looking setup. We once again want to write the parent function y equals f of x, given that the derivative equals x times quantity 1 plus y squared over y, and they give us the initial condition f of 0 is -3. Our setup, our overall plan here is exactly the same as the previous problem. The algebra that we encounter, I believe, is going to be a little different. but the overall scope isn't any different. We need to separate the variables first. So I'm going to partner y with dy, and I'm going to partner dx with all this stuff. And I know that doesn't completely separate the variables yet, but we're getting a little closer. I'm now going to divide away this stuff. And that'll just leave me with x dx on the right. Now I'm ready to integrate. Once the variables are separated, you can integrate. I think u sub is going to be our friend on this side, because du would then be 2y dy. That contains the numerator of the original integrand. We do need to put a 1/2 out front because that 2 constant that showed up is not part of the original problem. The 1/2 will equalize that. We've got du over u then, just like our previous example. On this integral, though, that's a little more happy and familiar. That's just a power rule, x squared over 2 plus constant. That means this is going to be 1/2 natural log of u, which I'm just going to call 1 plus y squared. And now we can go about figuring out how to isolate the y. Again, if you wanted to at this point, you could certainly plug in 0 for x, -3 for y, and then get a value for c, and then just you'd have a number to use and change throughout the problem. I'm going to hold off. It doesn't matter. I don't have a preferred way of doing it myself. It depends on which way the wind's blowing that day. For now, I'm going to leave it as c. I'm going to multiply every term by 2, and that'll get rid of this half as well as this division. So we'd have natural log. I know this is now 2c, but again, a constant's a constant till you know what it is anyway. And again, just like in the last problem, we can write this exponentially. We could write this as e to this power equals 1 plus y squared. Look, this is all, it doesn't matter if y is positive or negative. This result will, because you're squaring it, you're always going to get a positive result, meaning these absolute value bars don't mean anything. So, yeah, okay, sorry. So we can just kind of disregard them in this case. We do want to subtract 1 from both sides, so we'd have e to the x squared plus c. Better yet, I'm going to call this e to the x squared times e to the c, and then minus 1 equals y squared. Because again, e to the a plus b, 2-term power, you can split that up and say e to the first thing times e to the second thing. That means this is just a constant. So I'm going to call this constant times e to the x squared minus 1. At this point, I guess this is probably as good as any to figure out what c is supposed to be. Let's plug in that initial condition. If I plug in 0 for x, I get c times e to the 0, which is just c times 1, minus 1 equals y squared is -3 squared, which would be 9. So c minus 1 is 9. That means c is 10. Now, I still don't have the y isolated, because I still got y squared. But it's coming together a little nicer. I've got 10 for c. E to the x squared minus 1 is y squared. If I want to get the y by itself, I need to put in a square root sign. Now, here's the thing that people forget. When you put a square root into a problem where there had not been one, you need to consider both the positive and the negative branches. So in this case, I'd maybe have plus minus square root 10ex squared minus 1 for my answer, except that this wouldn't be a function. If you graphed this, the positive branch would be the top half of a parabola. The negative branch would give you the bottom half of a sideways parabola. We need to commit to one or the other, and the way that we decide which one to use is we go back to what was that initial condition. they give us the ordered pair 0, negative 3. You'll notice this is a negative y value. In order to get a negative y value when you have a square root in front would be to use only the negative branch. So because of that initial condition, I know I really just want the negative branch for my particular solution. So it's hard to give you examples of every kind of integration you could ever see. That's the bad news. The good news is you have seen them all before, so maybe dig deep through the resources that you have. It'll be a good review for the AP test coming up, and if you're still stumped, let me know.